Hi everyone, so my name is Yasuhiro Hasegawa from Taiwan. So I'm currently a postdoc at the AIA, but in this talk I'd like to discuss about one of the most important results of my PhD thesis work. So actually I finished up my PhD thesis work in the last year, so I think should be fair enough to discuss these things right now. Alright, so let's start from the observations. So as we discussed in yesterday and today's, so basically many next generation telescopes are available, right? Like a Subaru SMA or Herschel OMA. And these observations basically show that disks are rich in their structure. So I don't want to repeat these things, but I'd like to draw your attention once again about this beautiful picture taken by the SMA. So basically in this plot, 13 CO column density is shown by shown by the other function, the distance from the central star. And as you can see, so basically if you look at the CO ice line, then surface density is significantly dropped. This is because the condensation of the CO onto the dust grains. Alright, so definitely OMA has a better resolution about it. So that's why we are expecting we are going to have the more and more data about it. So probably the interesting key question is so what's the effect of this kind of structure or disk inhomogeneities on the planet formation? Alright, so this is the question we'd like to address right now. Okay, so then basically I'd like to focus on planetary migration. This is because planetary migration is one of the biggest problems in the theory of the planet formation. Actually, Richard Alexander gave us excellent review, so that's why maybe I don't need to go into the detail, but just let me give you the rough idea. So basically, planetary migration arises in a tidal torque between the planet and surrounding gas disks. So here's a nice simulation done by the Massey 2002. So if you put the planet in a gas disk, then you're going to have the density wave like this. And this density wave basically transfers angular momentum between the planet and the disk. And then planet basically migrates through the disk. Alright, and if you look at the literature, then basically planetary migration is highly sensitive to the disk structure. So which means it's very difficult to systematically study the study the effect of the planetary migration on planet formation. So that's why planetary migration is a kind of the biggest problem. Alright, so in order to circumvent this problem, or maybe solve this problem, we'd like to focus on a very interesting idea, which is a planet trap. Alright, so before going into the details, so actually I'd like to summarize some kinds of literature. So if you look at the homogeneous disk, which means basically disks are represented by the parallel, then you are going to have the steady inward or outward migration depending on your optical depth. All right. But as we know, basically disk. But if you look at the observation of the protoplanetary disk, or maybe if you start from the star formation to form the disk, then definitely we are going to have some kinds of inhomogeneities or maybe some kinds of structures. And if you incorporate these kinds of inhomogeneities, then we are going to have the planet trap. All right, so this is a kind of the key idea. All right, so to explain this idea, at first I'd like to focus on the dead zones. All right, so what's a dead zone? So basically, a protoplanetary disk is ionized by the X-rays from the central star and the cosmic rays. But if you look at the mid plane, so basically column density is so high. So that's why the ionization rate in this regime is significantly suppressed. So then coupling between the magnetic field becoming poor. So that's why MRI. So magnetorotational instability becoming inactive. And then you're going to have the low turbulence. So, and if you adopt some kinds of very famous prescription, which is basically which characterize the strength of the turbulence, then if you look at the surface of the disk, then you're going to have the high value of the alpha, because in this regime, basically MRI is very active. But if you look at the mid plane, then once again, ionization rate is suppressed. So that's why we are going to have the low value of the alpha, which is so-called the dead zone. All right. So and in a previous many past study, previous studies show that dead zone play lots of the interesting role in the disk evolution. And in this part, I'd like to focus on the thermal structure of the disk with the dead zone by performing the radial transfer calculations. All right, so here's the result. Also, basically, this plot shows the dust distribution, and basically color represents. This is the gas distribution, and basically color represents the density, and I'm not sure you can see, but the contour represents temperature, and of course, right now we'd like to consider planetary migration. So that's why we put the planet here, and this semicircle represents the hill radius of the planet. And in order to get the result, we basically use the RADMAC, which is a 2D Monte Carlo based radial transfer code that was mainly developed by the Keith Drummond at Heidelberg, but we modified a lot. And then, if you like to interest in the temperature, then basically grain size play an important role. So we did some kind of parameter study and find out that basically if you consider the 15 size grains from the 0.01 micron to the 1 millimeter, then the temperature structure is basically converged. And in this case, we consider value of the alpha equal 10 to minus 2 for the active region and 10 to minus 5 for the dead zone. And as you can see, so basically, if you incorporate a dead zone in the disk model, you're going to have the dusty wall at the outer edge of the outer dead zone boundaries. And this is because basically this is because of dust settling. So basically, dust is settled by the dust settling is controlled by the two things. One is the size, grain sizes, and the other one is the strength of the turbulence. And in this case, if you focus on the dead zone, then strength of the turbulence is significantly suppressed. So that's why these guys settled into the midplane very efficiently. But beyond that, still turbulence is very effective. So that's why we are going to have the dusty wall. And by performing the radial transfer calculation, we found out that basically dusty will lead to the efficient absorption of the sterile radiation. And this basically affects the disk temperature significantly. So let's see the temperature of the midplane more carefully. So basically this is the temperature of the midplane as a function of the distance from the central star. So if there is no dead zone in the disk, then you're going to have the disk structure like this. So basically temperature is decreased if distance is decreased. But if you put the dead zone, then basically we are going to have the dusty wall here, and this dusty wall is efficiently hit by the sterile radiation. And then that dusty wall lead to the backward heating. So that's why we find out that there's a positive temperature gradient in the temperature structure of the midplane. And if you adapt this structure and calculate the migration time, we get result like this. So definitely, as you can see, at a certain point of the positive temperature gradient, we got to the outward migration. So if you put the planet here, then basically planet is migrate towards the central star very quickly. But at this point, migration time become long. So that's why migration is become slow, but still moving inward, right? But at this point, basically, direction of the migration is reverse. All right, so this is the basic idea of the planet trap. So once again, if you incorporate the disk inhomogeneity, then basically disk structure is changed somehow. So then planetary migration is very sensitive to the disk structure. So that's why planet is trapped at this point. Okay, so this is a key idea. So and I hope I could convince you how useful the planet trap is. So. And at that time, there are a number of the candidates was proposed, so that's why we'd like to generalize this idea to consider the formation of the planetary system architecture. So, and basically, we'd like to consider three of them, and also for the generalization, we'd like to consider mass dependence, stellar mass dependence on the planetary system. All right, so let's go step by step. So basically, we already discussed the dead zone, so maybe we don't need to discuss. And ice line is one of the most famous one in our community, right? So maybe we don't need to discuss. And the last one is pretty much new, so that's why I'd like to discuss this one. All right, so basically, protoplanetary disks are heated by the two sources. One is the viscous heating, and one is the stellar radiation. Okay, so here's a very famous work done by the Yasuhiro 1998. So basically, in this plot, you're going to have the temperature of the midplane as a function of the distance from the central star, and and as you can see, basically, viscous heating is dominant in the inner region and gives you the steeper temperature profile. But if you look at the outer region of the disk, then you are going to have the stellar radiation become dominant, and you are going to have the shallower temperature profile. So definitely, some kinds of heat transition exists. And now we know what the disk inhomogeneity is. So now we'd like to confirm, whether or not this kind of the inhomogeneity becomes a planet trap. So in this study, actually, we'd like to do the very comprehensive work. So that's why we rely on the analytical approach, and to give you some idea how we confirm the how confirm disk inhomogeneity becomes a planet trap. So just let's focus on the Lindblad talk. All right, so which basically generates planetary migration. So basically, total Lindblad torque is characterized by these four functions. One is the mass of the planet, one is the mass position of the planet, and this is the surface density of the gas, and the last one is the temperature. And as we discussed, basically we know that some kind of structure or kind of behavior of the disk inhomogeneity. So that's why we adopt some kind of analytical modeling of them, and then we basically perform the Taylor expansion in terms of the scale, aspect ratio that is defined by the pressure scale height divided by the position of the planet, and then we get this kind of the result. Okay, so basically, gamma L naught is not so important because this is just a factor. So everything is just confined in epsilon. So which means basically direction of the migration is determined by the epsilons, and also some kinds of information of the disk inhomogeneity also condensed into the epsilon. And then we found out that basically, epsilon is 0, so which means the net torque is 0, so which means at the disk inhomogeneity. So which means basically, once again, if you incorporate the disk inhomogeneities, planet stop there. And recently, 2D hydro simulation confirms that the outer edge of the dead zone, the heat transition becomes a planet trap. So that's why we are very happy about it. Definitely, our analytical study gives you some kind of guide to understand what the planet trap is. And also, we find out that the position of the planet trap is very sensitive to the disk structure, such as surface density. All right. So then, if you combine all of them, we are going to picture like this. All right, so basically in this plot, position of the planet trap is shown as a function of the accretion rate, and basically dead zone is located in the innermost, and the ice line is the middle, and the heat transition trap is in the outermost. So based on this study, we find out the single disk model has up to 3 types of the planet traps, and also the movement of the planet trap is really depend on the accretion rate. Okay, and once again, we like to generalize our approach. So we did a parameter study for the stellar mass. So if you look at the massive case, basically planet trap distribute from the 4 AU to the 800 AU. And this, I think this number is interesting because direct imaging method detects the planet at this point. And if you consider the CTTS case, then the distribution basically shrink to the roughly 40 AU. And then if you look at the M stars, then maybe any planetary system could be confined within the 4 AU. So which means basically stellar mass and accretion rate establish a preferred initial scale of the planetary system. That is, I think it's very interesting. All right, so and combine these things, so we can draw some kind of picture of how planetary system is formed. All right, so this is a very schematic picture. So we do not model for the planetary growth, but I'd like to give you some rough idea. So basically, if you look at the early stage of the disk evolution, then basically, protoplanet is distributed with wide distance. Also, the mass of the planet should be very low. But as time goes on, planet is grow, and also disk is evolved. So that's why separation between the protoplanet should be become small, and also mass of the planet become high. All right, so what's next? All right, so basically we now just give you some kind of a framework of how planet formation is affected by the planet chart. So now we'd like to do some more exercise. So at first, maybe it's interesting to consider what's the effect of the planet chart or disk inhomogeneity on the planetary population. Actually, that was already done, and actually Ralph give us a talk tomorrow. But so I don't want to go into the detail. But if you calculate the evolutionary tracks of the planet, basically all the endpoint basically line up with the observation. So actually that is really nice. And also another interesting project is what's the effect of the planet trap on the planetary system architectures? And then, as we discussed, basically, our position of the planet trap converges to the single point at certain time. So, which means that definitely planetary, the dominant physical process change from the planetary migration to the dynamics. And the last one is what's the effect of the disk inhomogeneity onto the observer, such as SED or image. And as we discussed before, basically if you incorporate the disk inhomogeneity, we can show some kind of future like a positive temperature gradient. And now I'm working on calculating the SED project. So I think maybe OMA can detect some kind of future. So actually, Richard Alexander said, we don't know the connection between the disk evolution and the planet formation very much, but that is true. But I'd like to emphasize, if you consider our disk inhomogeneity and our planet chart, then we can beautifully make a bridge among these things. So that is very nice. And here's a summary. All right, so yeah, thank you so much. Thank you very much for your attention.
Okay, got time for a few questions. Anyone? No? Okay, well, thank you again.